The next step is to analyze the data, and we do that through graphing and looking for numbers that are very far away from the other data points, which we call outliers. And then we want to summarize the data, such as finding the measures of center, like the mean, the median, the mode, the mid-range, measures of variation, such as variation and the standard deviation, and measures of position. Calculations will be covered in more detail in Chapter 3. We also look at the distribution of the data. Is it a normal distribution, a bell-shaped curve, or is it skewed in some way? Or perhaps it's a uniform distribution. Are there any missing data? Is there something that should have been collected that wasn't? And are there any subjects that refuse to respond? So that's important to know any data points that may be missing in that regard. And then we apply statistical methods to determine if the values we calculated have some meaning or significance. Now, we will be using technology in some respects to find some of the calculations, but we will also be using some formulas and some information from the charts and the formulas and charts packet to conduct the statistical analysis. So after completing the preparation by looking at the context of the data, the source of the data, and the sampling method used to collect the data, we start that analysis process. There are some graphs that we'll be creating and analyzing in the next section, or in the next chapter, I should say, Chapter 2. And then in Chapter 3, we'll begin applying statistical methods that that a good statistical analysis really doesn't require that you have strong computational skills, although in this course you are going to be practicing using formulas to find some of the values. You do need to have use of common sense and pay careful attention to the statistical methods that are used to make sure that they're sound when analyzing the data. So the graphing part of it, we're going to be creating dot plots, histograms, stem and leaf plots, frequency polygons, scatter plots, etc. And again, those will be covered in Chapter 2. Further explorations of the data would include, as I mentioned already, calculating mean, median, mode, mid-range, variation, standard deviation, and we'll begin those calculations in Chapter 3. The main thing to take away from this section in regards to analyzing the data are the potential pitfalls that you'll run into. First, misleading conclusions. When you form a conclusion based on statistical analysis, you should make sure the statements are clear, even to those who don't have a background in statistics and know the terminology. The sample data, is it reported by the respondent, or is it actually measured? So you have some bias that is included potentially in reported data, such as if you conducted a survey of your classmates to determine, the mean weight of your classmates, and you asked them to tell you how much they weighed to the nearest pound. There could very well be some bias in the reported measurements that you receive, whereas if you could, in a non-COVID area, obviously, get together and actually take the measurements yourself by weighing each individual to collect the data, that would be unbiased. And then loaded questions. So are the questions in a survey worded in such a way that they would have a respondent reply in favor or in opposition to whatever the topic is at hand? So wording in a question needs to be very neutral and should not contain any bias. Ordering of a questions. Sometimes the order in which a survey's questions are arranged can have an impact on how respondents will reply. So you've got to take a look at ordering of the questions in a survey when you're analyzing the data to make sure there isn't any bias because of that pitfall. Non-response. So when a subject refuses to respond or isn't available, you have to take that into consideration in your analysis of the data. Does that impact your analysis? So for example, we collect data on student performance and student learning outcomes in a particular course and at the college level. What we do when we look at the data is we make a note that there are potentially some students who have not responded, and we consider that when we conduct an analysis to determine proficiency levels. So you have to think about how the non-respondents come into play when you're analyzing your data. And then percentages. Now percentages, they can be misleading if they're cited incorrectly. So that percentage value is misused more times than not. So again, if you have 100% of some quantity, you have all of it. So making a reference in which something exceeds 100%, they're not usually justified. So just be careful. And when you're analyzing data, you're self-reporting the percentages, and then when you're analyzing someone else's results and their use of percentages to see that they're accurate. So because percentages are widely used throughout statistics, having a decimal representation of a number, a fraction representation of a number, and a percentage representation of a number are very important. You need to review and refresh your memory on how you convert from a fraction to a decimal percent and, each one to the other. So there are some practice problems in this section that will have you do some conversions. And again, just to remind you, if you want to find the percent of an amount, you replace the percent symbol with division by 100, because percent means per 100. And then the interpretation of is multiplication. So this example shows 6% of 1200 is 72. 6% of 1200 responses. 6 over 100 is the 6 per 100, 6% of is times 1200 is the total number of the sample size, and then the 6% of 1200 would be 72. Let's say that it was in favor of whatever you were looking for. To convert from a decimal to a percent, you multiply by 100%. So if you had 0.25 as the decimal number, you would multiply that by 100 with the percent symbol to get 25%. And here's the calculation in symbol form. To convert a fraction to a percent, you divide the bottom number, the denominator, into the top number, the numerator, to get an equivalent decimal number. Then you multiply it by 100%. So this example shows the fraction 3/4 or 3/4. It's equivalent to 75%. So 3/4 as a decimal number, 3 divided by 4 is 0.75. You take 0.75, multiply it by 100%, and that equals 75%. To convert from a percentage to a decimal number, replace the percent symbol with a division by 100, and then complete the division to get the decimal equivalent. So 85% would be 85 over 100, which equals 0.85. Conclusion. So remember, at the beginning of this section, we discussed the fact that we were going to cover the 3 main general brushstroke topics in the study of statistics. And the first thing you do is prepare by looking at the data, context, source, and sampling method. Then you're going to analyze the data, display it, do some number crunching, find some calculations, and then all of that leads to making conclusions based on the data. And the 2 main points to focus on in this part of this section in regards to conclusions is there a statistical significance evident in your analysis? And if there is, you have to consider, is it practical for that to be significant? So I'll show you this by example. All right, so when we look at statistical significance, let's say that in a study, the likelihood of an event to occur by chance is 5% or less. We say that it's statistically significant. Getting 98 girls and 100 random births is statistically significant because such an extreme outcome is not likely to result from random chance. Now, the 98 and 100, right now ignore that 5% value, because what we're looking for is, does this seem out of the norm of what you would expect? Well, if you think about having a specific child of a specific gender in a birth, generally you either have a boy or a girl, and there's a 50-50 chance of having either gender. So therefore, out of 100 births, you would expect 50 or so of them to be girls. Well, if you get 98 out of 100, I mean, something's happening to cause that many girls to be born out of 100. That's not just by chance, because by chance there should have only been 50 out of 100 girls. So we would say that is statistically significant. Later on, we'll be calculating the probability or likelihood of that occurring, and then that's where the 5% comes in, 5% or less. The second bullet point here is getting 52 girls in 100 births. Okay, so that is not statistically significant, generally speaking, because remember that in 100 births, you would expect 50 girls. But in 100 births, when you get 52, well, that's still pretty close to 50. Now, as the number of births increases, you would expect to be more at the 50% mark. But here, 52, 50, 48, somewhere in that 50 range does not seem to be anything unusual going on. So we say that it is not statistically significant, because that could easily occur by chance. Practical significance. So even if you conduct a study and you, find your probability the event occurs, and you determine that that event is unusual, it wouldn't happen by chance, so you decide that there is statistical significance, maybe there's not practical significance in the application of that analysis. So here's an example to show you the difference between statistical significance and practical significance. So we're back to childbirth. And ProCare Industries, a company, once supplied a product named Gender Choice. It supposedly increased the chance of a couple having a baby with the gender they desired. Well, suppose that the product was tested with 10,000 couples, and the results were 5,200 baby girls born in those 10,000 births. Now, 52 out of 100 wasn't statistically significant, because you would expect around 50 out of 100. But if you think about 10,000 births, remember, as the number of births increases, that numerator may take on a different significance level in relation to the denominator, the total number of trials. So we would have expected about 5,000 out of 10,000, but we ended up with 5,200 out of 10,000 births that are girls. When you find the probability of having 5,200 girls out of 10,000 births, the number is 0.003%, which now we're going to use that 5% mark. So since that event occurring, having 5,200 out of 10,000 births end up as girls, is 0.003%, which is less than our 5% default value, that would happen by chance, then it seems there's something affecting the gender in a birth. So the 5,200 is statistically significant. Okay, so let's talk about practical significance. So Okay, so now you have 5,200 out of 10,000 couples. We have determined that the extra 200 girls, what we would have expected to be 5,000 out of 10,000 girls, we have an extra 200. Well, that's not a lot. If you really want to have a baby girl and you're using this product to increase the likelihood of you having a baby girl, you would probably want the results of this study to be somewhere, around 7,500 baby girls were born out of 10,000 births. So although the 5,200 out of 10,000 does seem that that wouldn't happen by chance, and so it's statistically significant, it doesn't have practical significance. Because why would you spend a lot of time, energy, and money using a product that is only going to perhaps end up affecting the gender of your child when it's, during the conception and when it's born? So that is basically a simple comparison between what does it mean to be statistically significant. We do the number crunch and we compare against the numbers. Oh, the numbers say it's statistically significant, but then back away from the problem and take a look at it in the context of it. Is it really practically significant? And if you say no, then you've done some number crunching, which is great. You can state that with some firm conviction, but it really does have no practical significance in the context of the problem.